Hi, this is Rebecca, and today I'm going to be going over forces. So basically what I didn't understand on the forces test and what I missed most of was questions on tension forces, forces on incline, and there was a free response about kind of labs and what to do with that. So I'll be covering these three topics. So first was a 2012 Physics B free response problem on forces, and tension forces specifically. So the question reads, block A of mass 2 kilograms is pulled along a horizontal table by a force of 15 newtons, which is applied by a light string that passes over a light frictionless pulley as shown above. The coefficient of friction is between the block and the surface is 0.25. Okay, so part A says on the dot below, which represents the block, draw and label the forces, not the components that act on the block as it's pulled across the table. So this one, since we can see it's on a horizontal table, the free body diagram is pretty basic. You have your gravity going downwards, and your normal force should be equal to gravity going upwards, and your tension force is greater than your friction force. And your friction force is always moving opposite of your applied or tension force. So part B says calculate the magnitude of acceleration of the block. So what we're going to do is we'll say the sum of the forces equals, in the x direction, is F of the force of tension minus the force of friction. And then we move over here to calculate the force of friction, and that's just the coefficient times the normal force. So we find that the normal force is equal over here, is equal to the opposite of gravity. So that's mass times gravity. So then over here we just plug in, earlier they told us our coefficient was 1/4, and we multiply that by mass times gravity. And then we plug that back in over here. So our force of tension they gave us was 15 newtons, which is shown on the diagram right there. So we say 15 newtons minus mass times gravity over 4. Same thing as a quarter, I just wrote it out like a fraction. And then we plug in all of our numbers, and we find that the sum of our forces is about 10 newtons. But then we still have to remember the sum of our forces is always equal to mass times acceleration. So we have mass times acceleration over here, and then we can divide, our mass is 2 kilograms, so we divide by that on both sides, and our acceleration is equal to approximately 5 meters per second squared. So now we have parts C through F, and they changed the diagram slightly. So this now says the applied force is removed. Block B of mass 1.5 kilograms is now attached to the string as shown above. The system is released from rest so that 1.5 kilogram box descends and the 2.0 kilogram block is again pulled across the table. So part C reads, calculate the acceleration of the 1.5 kilogram block as it descends. So I moved over here for part C, so we again set up our sum of our forces is equal to forces on A and forces B, so it's basically block A and block B. So you break that up into block A right here so we also, another thing to remember for pulley system is we define our horizontal x as going around the pulley. So this isn't y direction, this is still x, it just curves around the pulley. So we can say that our sum of forces on A is tension force minus our friction, which will be going the opposite direction. And then we also have, on B, we have gravity going down and tension pulling up. So we can say our sum of forces is equal to F of T minus F of friction on block A plus F gravity on B minus friction on T, or force of tension, sorry. And our tensions should cancel out because they're equivalent. So we'll have the sum of forces is equal to force of gravity on block B minus force of friction on block A. So we plug, we know that gravity is mass times gravity. So we just plug in our mass, which is 1.5. And then our friction is our friction coefficient times the block, and we found that earlier. So we're just plugging that all in again. And basically our friction, since it's 2 kilograms times a quarter is our coefficient, we just say it's 1/2 g is our friction. So we plug all that in and we have 1.5g minus 0.5g, and I just didn't feel like writing out 9.181, but that's what gravity is. And so when you have 1.5 minus 0.5, then we're left with just gravity, so 9.81 newtons is what our sum of our forces is equal to. And again, the sum of forces is equal to mass times acceleration. So 9.81, and then we divide that by our total mass, because remember, we're solving for the total forces on the entire system. So we have to add mass A plus mass B. So 9.81 divided by 3.5 gives us approximately 2.8 meters per second. So now part D asks, calculate the tension in the string connecting the two blocks. And this is where I used to really struggle, but I think I get it now. So we have our sum of forces, but we're not going to analyze the entire system this time. We're just going to look at block B. And we could do the same thing with A, but I just chose B. So sum of forces on B is force of gravity minus force of tension, because remember, the gravity is working downwards and the tension is going upwards. So we have mass of B times acceleration, because remember, sum of the forces is mass times acceleration, equals mass of B times gravity, which is our force of gravity, minus tension force. And we have, so then we can say our tension force is equal, that's a B, to mass B times gravity minus mass B times acceleration. So you can factor out a mass if you want to make it look simpler. And then we just plug in all of our numbers, and our acceleration came from part C. And so we have that F of t equals 1.5 kilograms times 9.81 meters per second squared minus 2.8 meters per second squared. And we're left with our total force of tension is equal to 10.515 newtons. Now, part E asks, calculate the distance that the 1.5 kilogram block descends in 4 seconds. So this is where it gets kind of fun, or tricky, I guess, and we now have to go back to our first unit and kind of think of those equations we used to have. So I chose the equations as change in x equals original velocity times time plus 1/2 acceleration times time squared. So our initial velocity is 0, so because we're beginning from rest, and so we can say our change in x is equal to 1/2 at squared. So we plug in our acceleration from over here, and we plug in, they gave us 0.4 seconds, and we plug in all those numbers and solve, and we get change in x will be about 0.244 meters. And now part F, and part F is asking kind of about lab questions, and I also struggle with this on the test. So it says, if the system is set up in a laboratory and the acceleration of the 1.5 kilogram block is experimentally determined, the experimental value is found to be smaller than the value calculated above. If the given value for the coefficient of friction is correct and air resistance is negligible, explain briefly, but specifically, why the experimental value of acceleration is smaller. So this is the similar kind of question that was on our test that I completely didn't get. So what I was thinking is, what you could say for this one is, the only thing that is not accounted for in the setup they give you in this problem that would happen experimentally is friction of the pulley, and that would basically be your change. So our answer would be that the experimental value of acceleration is smaller because the friction of pulley is working in the opposite direction, so it'll slow the descent slightly of the block B. Okay, so that was the 2012 Physics B free response, and now we're going to look at forces on an incline. So this says, so we have a little guy pushing a block up a hill, and it says a box is being pushed at a constant speed up an inclined plane at a vertical height of 3 meters above the ground, as shown in the figure above. The person exerts a force parallel to the plane. The mass M of the box is 50 kilograms, and the coefficient of friction between the box and the plane is 0.3. And part A says, on the dot below that represents the box, draw and label the forces, not the components acting on the box. So again, this is similar to what we did before, just a little trickier because you're on an incline. So you have to remember your normal force is always perpendicular to your plane, and then your applied force is obviously going to be parallel to the plane, and then your friction force will be working in the opposite direction as your applied force. But then the tricky part is gravity is always perpendicular to the ground, so it's not perpendicular to the plane at this point. So we just have to remember that gravity is actually in two components, but as I said, don't draw it on here. So then part B asks, calculate the normal force of the plane on the box. If you need to draw anything, use the space below. Basically, don't draw your components up here. So I moved to some extra paper for part B, and we look up here. So we say this, so I kind of redrew it up here just with the components because personally I like visualizing it. So our sum of forces in the y direction is our normal force minus our force of gravity, the y component. And so we can say they're equal to each other because the problem said it's at a constant speed. So we know that our acceleration is 0 because our velocity is constant. So we end up setting those equal to each other. So our normal force is equal to the mass times gravity times cosine of 20 degrees. And we plug in all of our numbers. Our mass is 50 kilograms, and we solve for our normal force is equal to 460.9 newtons. Now, part C says, calculate the component force of gravity acting on the box that is parallel to the plane. So again, this diagram over here helps me. Our x component is what's parallel to the plane. So this is basically just solving for the opposite component that we solved for earlier. So the FG, that's a little parallel sign. So the parallel force, or is basically the F, is the gravity x component force. So we can say the force of the x component of gravity is equal to mg sine 20 degrees. And you just have to look at the angle and figure out if your side is opposite or adjacent to figure out if you use sine or cosine. And then we can say Fg of x equals 167.76 newtons. Now, part D asks to calculate the friction force between the plane and the box. So we say the F of friction is equal to the coefficient times the normal force, and we just calculated the normal force right here. So we plug that in. They told us our coefficient was 0.3. We plug it into our calculator, and we get 138.27 newtons. Now part E is where it'll get a little trickier, and part E says calculate the force applied by the person on the box. So we again set up our sum of forces in the x direction, and then we have our force applied, because our force applied by the person, minus the F of g of x. Remember, it's not just gravity. We have to look at this component of gravity because that's working the opposite direction as our applied force, and then subtract our frictional force. So we set all those equal to mass times acceleration. Again, velocity is constant, so our acceleration is 0. So we can say that force, the applied force, is equal to the x component of the gravitational force plus the frictional force. And we solved for the x component of the gravity force and the frictional force right here. So we just add these two numbers and plug it all in right here, and we'll get our applied force is equal to 306.037 newtons. Part F is probably the hardest part of this problem. It says calculate the work done by the person pushing the box, assuming the box is raised to the vertical height of 3 meters. So I don't think by this unit we had done work yet, but I don't really remember. But anyways, we've covered it now. So work is equal to the parallel force times distance. So we have to use our sine rules and say that sine of 20 degrees is equal to opposite over hypotenuse, so 3 meters over our distance. Solve for distance, and we get 8.77 meters. And then we can say work equals force, our applied force times distance, and our applied force we'd solve for right over here. Plug that in, plug in our distance, and our work is 2,684.37 joules. So I have gone over how to figure out tension forces, force on incline, and lab free response questions. Hope this helped.